When people discuss MOSFET modeling, the main focus is usually the steady-state current voltage equation of a MOSFET. The charge voltage model is less frequently being touched upon. Therefore, I will give a more detailed example on how the simple classical MOSFET charge model are being developed. Even the simplest charge model is already quite complicated compared with the basic current model. Even though I'll spend quite some time on the charge model equations, I would like to emphasize that the purpose of this presentation is not to provide a detailed description on the device physics of a MOSFET. Therefore, the model developed here is still quite primitive, and I will not spend time to explain the origin of some of the equations. Instead, you should focus on the general modeling methodology. At the same time, I would like to illustrate that even with the recent advancement in compact model development, some fundamental issues in MOSFET charge models are not fully resolved. These issues will also be explained in this presentation. For a MOSFET with the symbol given here, each terminal is considered to be a charge storage node with a charge component associated with it. We label the charges associated with the terminals of the MOSFET to be QD, QG, QS, and QB respectively, as shown in the figure. The physical components of the charges are illustrated in the figure below, which consists of the gate charge QG, channel carrier charge QC, and substrate depletion charge QB. Here, the channel charge QC refers to the carrier charge coming from the source and drain terminals. Eventually, we need to partition it back to QS and QD. The process is quite complicated, and we'll work with QC for the time being. The partition of QC back to QD and QS will be discussed later. As the MOSFET is expected to be charge neutral at all times, the magnitude of the gate charge must be equal to the sum of the magnitude of the channel carrier charge and the substrate depletion charge. Therefore, if the value of two of the charges are known, the third one can be derived accordingly. In this example, we will derive the expression for QC and QB, and the sum of the magnitude will give the magnitude of QG. Or more generally, the charge neutrality can be represented by the equation given here, that the sum of the total charges of all terminals of a device must be equal to 0. To derive the numeric values of the charges, we first assume the drain voltage is very small and close to the source voltage, and the source voltage is assumed to be ground. In this case, the charge along the channel is more or less uniform. Conventional knowledge of the MOS capacitor can be used to derive QB and QC. Let's recall our knowledge of MOS capacitor that we learned from some common textbooks. The charge distribution as a function of gate voltage is given in the figure below. Some people may be more familiar with the series characteristics corresponding to the MOS capacitor, which is also given here. From both figures, we can see that there are three different types of charges described by different equations. We will deal with them individually. We start to derive the charge equations from the accumulation region, which happens when VGB is more negative than the flatband voltage. In this case, the charge in the channel is mainly composed of holes from the substrate. So, the accumulation charge is associated with the body node, and we label it as QB. The situation is relatively simple, as the MOSFET can be treated as a parallel plate capacitor. Therefore, QB is just equal to minus Cox WL times VGB minus V-flat band. As VGB is more negative than V-flat band, the quantity in the parentheses is negative. So, the overall sign of QB is positive for whole charges. If the source is taken as the reference 0, we can rewrite the equation by referencing the gate voltage and substrate voltage to the source voltage explicitly. The equation will become what is shown here. In accumulation, the source and drain are cut off from the channel, and therefore can be ignored. That also means that the channel charge from the source and drain, QC, is almost 0. The gate charge QG is equal to the sum of QB and QC with opposite sign, which is given by the equation here. The charges in the accumulation mode are independent of the drain voltage. Now, we will derive the charge in the subthreshold regions with the gate voltage between the flatband voltage and the threshold voltage. Similar to the accumulation case, the source and drain are cut off from the channel, and therefore their effects can be ignored. So, the channel carrier charge QC from the source and drain is also zero. The charge in the channel region is composed of depleted dopant ions associated with the body terminal. So, QB is given by the depletion charge. The depletion charge is given by the doping concentration times the depletion width as shown in this equation here. Na represents the doping concentration, and XD represents the depletion width. The depletion width can be found with the equation given here expressed in terms of the surface potential phi s. Putting XD back to the equation, we have QB given by this expression. From the modeling perspective, this equation is difficult to use because it is expressed in terms of an intermediate variable phi s. In order to calculate the entries to the Jacobian matrix for circuit simulation, we have to express the charge explicitly in terms of terminal voltages. So, we have to eliminate phi s. To do that, we can relate phi s and Vg using the equation given here. Substituting phi s from the second equation into the first equation, we can solve for the depletion charge QB, which is given by the expression here. In this equation, gamma is the body factor. If the source is taken as the ground reference, we can insert the source reference into the equation, and it becomes what is given. To ensure its correctness, we should check for the continuity with the accumulation region at Vg equal to V flat band. Checking the expression at VGB equal to the flatband voltage, both equations gives QB equal to 0, which is continuous. As the channel charge is 0, the gate charge QG is just the body charge QB with an opposite sign. In the subthreshold region, QB has a width dependent on the drain voltage VD, as the depletion region width near the drain increases with the drain voltage. However, this will not be discussed here, as we are not aiming to develop an accurate model. We will keep our focus to explain the process to develop the charge model. You may find the refined model from other articles. For now, we just assume QB and QG are more or less independent of the drain voltage in the subthreshold region. In the strong inversion mode, the MOSFET can operate in the linear region or saturation region. We will first deal with the linear region having a gate voltage above Vt and a drain voltage smaller than the saturation drain voltage Vd set. As the channel now connects the drain to the source, the channel voltage will increase along the y direction from 0 to the drain voltage. We denote the channel voltage at the particular location y as Vy. The body charge at the particular location y is determined by the threshold voltage at that point, given by the equation here. The surface band bending phi s in the equation increases in the y direction from the source to the drain, as illustrated in this 2D band diagram given here, after flipping the MOSFET by 90 degrees. Knowing the band bending at the source is equal to 2 phi b, we can write phi s equal to 2 phi b plus Vy at the location y. Vt also increases along the channel towards the drain due to the increase in the depletion charge. We can write Vt equal to Vt0, which is the threshold voltage at the source, plus alpha Vy, where alpha is usually called the bulk charge factor. Putting the last two equations to the expression of QB, we obtain the equation of QB at any location y. In this equation, Vt refers to the threshold voltage at the source. To find the total body charge, we have to integrate small qb along the channel from the source to the drain using the integral given here. The integration cannot be performed directly, as we do not know the relationship between Vy and y. We need to change the integration variable. To do this, We recall that the drain current of a MOSFET is equal to the carrier charge density at any location y times the velocity at that particular location, as shown in this equation. And the velocity of the carriers can be expressed as the mobility times the E field. And we can further express the E field as dV over dy. With this equation, we can express dy in terms of dV, which is shown here. After substituting dy back to the integral, it becomes integratable. We will skip a few mechanical derivation steps. Finally, we obtain the equation for the total charge QB, which is given here. To calculate the channel charge, we know the amount of carrier charge at the location y is given by Cox W, Vg minus Vt minus alpha Vy. The bulk charge factor is included to account for the increase of Vt towards the drain with the increase of depletion charge at high Vd. We can integrate these expressions from the source to the drain and get the total channel charge. To perform the integration, again, we need to change the integration variable from dy to dv using the previously derived equation for dy. After the change of variable, the integral becomes what is given here. We can perform the integration and we obtain the expression of the channel charge Qc, which is given by this equation. Finally, the total gate charge is equal to the sum of Qb and Qc with an opposite sign. And its expression is given here. For the charge in the saturation region, we note that the saturation region is only the extension of the linear region by limiting Vds to Vdz. Vdz is given by Vg minus Vt in the simplified textbook model. As we are including the effect of drain voltage on the body charge through the linearized parameter alpha, Vdz is modified to become Vg minus Vt divided by alpha. Putting this into the earlier expressions of Qb, Qc, and Qg we derived for the linear region, we can obtain the following equations for the charge in the saturation region. It is interesting to note that the channel charge in the channel is Cox WL Vg minus Vt in the linear region with very small Vd, and eventually become 2/3 of the initial value in the saturation region. It may be more intuitive to understand the properties of the charges if we plot them with respect to different inputs. We first look at how the charges change with the gate voltage. For simplicity, let's assume the body is grounded and Vb equal to 0 volt. In the accumulation region, Qb is composed of the accumulated holes and is given by the expression here. Note that hole charges are positive. In the depletion region, when the gate voltage is smaller than the threshold voltage, Qb is given by this expression here, and it has a square root relationship with the gate voltage Vgs. When we enter the saturation region, Qb is given by this expression here. From the expression, we can see that Qb is linearly dependent on Vgs through the Vdz term. Finally, the MOSFET enters the linear region and has a much weaker dependence on Vg. It is almost flat in this region. For the channel charge, it is almost 0 when Vg is smaller than Vt. When Vg becomes larger than Vt, it increases linearly with Vg at the rate of 2/3 Cox WL in the saturation region. When it enters the linear region, the channel carrier charge increases with Cox WL Vg. The shape is almost a straight line with a steeper slope compared with the saturation region. Finally, the gate charge is the combination of both Qb and Qc with an opposite sign. All three charges are plotted together here for comparison. To see how Qc and Qb change with the drain voltage, we consider a gate voltage higher than Vt is applied to the MOSFET. Otherwise, in the suppressor region, the drain has no control over Qb, and Qc is just 0. At very small VDS close to zero, the amount of charge is given by the expression shown here. They are obtained by setting VDS to zero in the linear region charge equations. We only plot the magnitude of the charge and ignore the sign. When the drain voltage increases, QB increases and QC decreases because some of the QC is converted to QB. At the saturation point, the values are given by the equation shown in the graph. And the value of QC is always 2/3 of the initial value. After the MOSFET enters the saturation region, the charge will become a constant, with a value equal to that at the saturation point. The gate charge can be calculated by adding the two charges, and its characteristic is given here. So far, we are working with the channel charge QC. However, all charges should be associated with a terminal for circuit simulation. As the channel carrier charge comes from both the source and the drain, we have to divide the channel charge to the source and to the drain based on the origin and destination. The question is how? And this leads to the famous charge partition problem. And up to now, there's no perfect solution to this problem, and the real situation is difficult to verify by experiment. Based on intuitions, there are 3 different approaches to handle the charge partitions based on different assumptions. They are the 50-50 charge partition scheme, the 40-60 charge partition scheme, and the 0-100 charge partition scheme. All of them are not fully correct and only used to provide a guideline. The 50-50 charge partition scheme just equally divide the charge in the channel between the source and the drain. That is, the source charge QS and the drain charge QD are just simply equal to QC divided by 2. And graphically, it is illustrated in the plot given here. This approach is most accurate in the linear region with small VDS because the source and drain are symmetrical. But it will not be accurate in the saturation region with high drain voltage because the channel is no longer symmetrical to the source and to the drain terminal. When the MOSFET is operating in the saturation region, the drain is actually cut off from the channel by the pinch-off or velocity saturation region. In that case, the bottom plate of the gate capacitor is mainly connected to the source, as shown in the figure here. And all the channel charge should be associated to the source. To account for that, we can approximate the charge partition to change linearly with VD, from 50-50 at small VD to 0-100 when VD is equal to VDZ. By doing so, we can obtain the expression of QS and QD as given here, and their sum will be equal to QC. Graphically, how QS and QD vary with drain voltage is shown in the graph here. The 50-50 and 0-100 charge partition scheme represents 2 extreme cases, and both of them cannot fully describe the charge behavior of a MOSFET. For example, it was found that in the saturation region, the drain can still control some of the channel charge. To account for this, Watt and Dutton of Stanford University proposed a geometry-based charge partition scheme. They argue that the charge controlled by the 2 terminals should be the weighted sum with respect to the normalized distance where the charge is located between the source and the drain. Using this approach, we can write the drain charge and source charge in terms of the weighted sum of the charge times the distance from the terminals, which is given by the 2 integral as shown here. Performing the integrations, we obtain the expression of QS and QD as given here. Graphically, the resulting characteristic of QS and QD are given here. The source and drain charge in the saturation region become what is given in the graph, and the resulting charge partition in the saturation region is 40-60. While the proposed approach using weighted sum based on normalized distance is reasonable, there is no experimental validation to it. It is mainly due to the difficulty to measure how much charge the source and the drain terminals are controlling. Currently, the 4060 charge partition is the most widely used model, as it represents a trade-off between the 5050 and 0100 charge partition schemes. But it was found that the charge partition is closer to 0100 in the saturation region in fast transient. In practice, the charge partition depends on how fast the MOSFET is being turned on and off. I will discuss this in the coming videos.